Thanks, Tony, for inviting me here, and it's great to be back at EuroMPI. As Tony said, he had organized the Scalable Parallel Libraries Conference in Starkville, Mississippi, at Mississippi State. That was in 1994, and that's where I first met Tony and Puri, and even Bill and Rusty, and that's how I ended up at Argonne the following year, 6 months after that. So, that's how it kind of started. And my talk is titled 30 Years of MPI and Many More to Come. And I've sort of organized it as follows. I gave a keynote at EuroMPI 2013, which was held in Madrid, Spain. That was 9 years ago now. So I wanted to go back and sort of revisit some of the things I said there, some of the projections I made at that time to see what turned out to be okay or right, and what didn't. That might be instructive for the future in terms of how projections turned out. And then I want to cover some issues facing MPI today and going forward as well. And this will be from the application side, from the technology and system side, and from MPI itself, from say the MPI standard perspective as well. And how can we address those challenges and some additional thoughts in general. My keynote at EuroMPI 13, this was in September 2013. So in the June top 500 list in 2013, these were the top 5 systems at the time. It was Tianhe 2A in China, which was a Intel Xeon and a Xeon Phi based system. Sequoia at Livermore was a Blue Gene Q. It was a big Blue Gene Q. Titan at Oak Ridge, which was a Cray XK7, and that was the only in the top 5 at the time with GPUs on it. Then the K computer in Japan, and Mira at Argonne, which was another Blue Gene Q, which was half the size of Sequoia. And those were clearly pre-exascale days. These systems were in the 10 to 50 petaflops range. So those were pre-exascale days. And there was a lot of planning going on in terms of workshops and reports and all sorts of other activity about how do we get to exascale. And that was going on even before 2013. And we are now there. I mean, we have just reached exascale. The Frontier in the June list crossed an exascale. So we're now there, but at that time, it was all about how do you get there? And DOE's exascale computing project, which is a huge project in the US, that did not start until 2016. That was 3 years after this talk at that time. So my talk was about evolving MPI to address the challenges of exascale systems. That is, what is needed to get MPI ready for exascale. And the next few slides are directly from my talk, just to give you a flavor of what things were at that time. So already in those days, of course, all applications were using MPI, but they were increasingly using hybrid MPI plus OpenMP and MPI plus MPI plus threads in general. And there were also applications exploring the MPI accelerator or GPU hybrid. And the systems, in terms of the number of cores, excluding the GPU cores in those days, at that time, from the June top 500 list, if you rank them in order of that, the Tianhe 2 had over 3 million cores. The Sequoia had 1.5 million cores. Then Mira was half that size, and so on. If you go down the list, up to 300,000 cores was Titan. This is not including the GPU cores. So clearly, the number of cores were already quite large in those days, and MPI was already running at scale on those systems. So I had some slides about applications that were running on these systems, and so one was the hack cosmology code that Salman Habib leads at Argonne. That does cosmological simulations, and it continues to, and it still exists, and it is one of the exascale applications as well. So this was a Gordon Bell Prize finalist at SC12 the previous year. And this one ran on the full Sequoia system, the whole 1.5 million cores, using an MPI plus OpenMP hybrid, where it used 16 MPI ranks times 4 OpenMP threads on each node, which matched the architecture of the system, which had 16 cores per node and 4 hardware threads each. And you could not exceed the number of threads there. I mean, it was the software there was, you could have 16 times 4 or some combination and thereof. And this used the entire 6.3 million way concurrency with 1.5 million MPI ranks and 4 threads per rank. Then there was another code. This was also an SC12 Gordon Bell Prize finalist. This was a cardiac modeling code from IBM and Livermore that achieved 12 petaflops on Sequoia. And this one modeled a beating human heart at near cellular resolution. This also ran on the full system. And they didn't use the 16x4 combination. They used 1 MPI rank per node and 64 threads. And they used OpenMP just for thread creation, and the rest of the thread choreography and synchronization, they used custom code, not OpenMP pragmas. And this also got good performance and was a Gordon Bell finalist. Then there was another code, which was the Ross Parallel Discrete Event Simulator, which is from the RPI group, Rensselaer Polytechnic, Chris Carothers. And this code was all MPI, and they were able to run it not just on Sequoia, but there was a second system at Livermore called Vulcan, which was used for industrial collaboration, for partnership with industry. But they ran it at a time when those two systems were connected together. So it was 96 ranks of Sequoia and 24 ranks of Vulcan together as one system. So that had almost 2 million cores, and they ran it as all MPI with 4 MPI ranks per core. So they ran almost 8 million ranks of MPI at that time, and they got good results in the discrete event simulation space. So at that time, there were already applications running at large scale from an MPI perspective. And there was another group, Professor Alan Wagner's group at the University of British Columbia, whom we used to collaborate with, the MPICH group at Argonne used to collaborate with. And they had run programs with over 100 million MPI ranks only on a cluster that with like 6,000 cores. And they did that by using a modified version of MPICH that which they called FGMPI, fine grain MPI, that implemented MPI ranks as coroutines rather than OS processes. And the coroutines are like lightweight processes, but they're non-preemptive, so you have to actually yield to another process and so forth. But they were able to run with 100 million MPI ranks, and they also had some funding from Intel to continue that work. And so, the reason I mention all this is that's where things were headed in those days. And how do you scale MPI to very, very large number of ranks? And the other thing that was going on at that time were all sorts of projections or workshops and reports about what an exascale system might look like. And one of them was this thing from a DOE group, which was sort of got famous because they referred to it as 2 swim lanes, and that's somehow that word swim lanes caught on. So what they said that was you could reach an exaflop system in 2 ways. One is with nodes of 1 teraflop. Do I have it? Do I have that? Right, yeah. With node performance of 1 teraflop, and the number of nodes is 1 million, and then you can reach an exaflop. Or you have more powerful nodes that are 10 teraflops, and if you have 100,000 of those, you can reach 1 million. So that was their 2-point designs, or that's what these are experts who are coming up with these. So the first one on the left was somewhat like the blue gene systems carried forward. So you have large number of nodes, but the nodes themselves are not so powerful. And the second one is you have more powerful nodes with they weren't really considering GPUs, but maybe the power, IBM power type of systems, or the more beefier nodes that way. So that was the way to get to exascale. So the trends and projections. So is this blocking your view, or let me just see if I can. I should minimize this. Somehow I can't get rid of. It should go away normally. What's that? This one, right?
Online, we see your slide number 12.
Yeah, you can see our slides, but here they were seeing more than the slide. The zoom, they were seeing part of the zoom. It's a little better now, but the title is blocked. That should go away normally. I don't know why it's, but it's okay. So if I think I went ahead. Let me. Yeah. So the trends and projections in 2013 pointed to systems needing large numbers of cores and nodes. And so my talk at that time, as well as other research in the day, was what would it take to scale MPI to large system sizes? So these are some papers that several of us had written at that time. What about MPI on millions of cores, or what would it take to scale MPI to that size? And the issues there were, how do you reduce the memory footprint of the MPI library? How do you design it so that it doesn't scale linearly with the number of processes? And there were some issues even with the MPI standard, that some of the functions to take parameters like the V versions of the collectives take parameters that are in order, that are their size is the number of processes or the number of MPI ranks. So that itself is a big data structure to pass to MPI. So those were the issues under consideration at that time. But what the forecasts or the projections missed totally were that GPUs would become so prominent as they are now. And it was not that GPUs didn't exist at that time. They have existed at least, the GPUs have existed at least since 2005. And in 2013, at least one system, as I said, the Titan had GPUs, and Blue Waters also had GPUs for half the system, I think. So big systems existed with GPUs, and there was a lot of research and papers being written about how to do scientific computing on GPUs. In say 2005 to 2010, there were so many papers in that, because people were porting their scientific code onto a GPU, but getting only two or three times the performance. But if you did things right, if you mapped the problem correctly, you could get 100 times better. So the papers were about how do you get to the 100x. But no one actually predicted that the systems would be GPU based now. But as it turns out, if you look at this June's top 500 list, 7 of the top 10 systems are GPU based, and all 3 of the first 3 exascale systems in the US are GPU based, and it's not, and they are Intel and AMD based GPUs, not even NVIDIA GPUs. Although there are lots of other systems with NVIDIA GPUs, such as the Summit and Sierra and lots of other clusters and so forth. But with multiple GPUs on a node, each node becomes very powerful, and most of the flops are obtained from that GPU, and as a result, the system size is much smaller. Fewer total number of nodes are needed. And if you see the sizes, the CPU to GPU ratio on Titan was 1:1. On Summit at Oak Ridge is 1:3, and on Frontier is 1:8. It is a 1 CPU and 8 GPUs for each CPU. So that's where all the compute is coming from, the GPU. And so the total number of nodes, which was 18,000 in Titan, was just 4,500 on Summit, and Frontier is 9,400. Whereas the Blue Gene Q had like 98,000 nodes at the Livermore Sequoia. So this is like 1/10 of that size. So we are now dealing with a different problem. The MPI here doesn't need to scale to millions of cores or large number of nodes. The issue is now is about hybrid programming. So if the roadmaps had been correct at that time, then the focus would have been different. It would have been on the MPI plus GPU hybrid programming, on how MPI can play well or integrate or interoperate with the variety of node programming models we encounter now, which are like OpenMP offload. There's CUDA, there's HIP, SYCL, OpenACC, and there are others. There's Cocos Raja if you count them. So we could have had a 7-year head start on this. There is work happening now, and MPI implementations are also trying to do a better job with GPUs. There is work in the accelerator working group, or the hybrid working group, about how to do better with GPUs. There is a paper at this meeting that we will present this afternoon about that. There's other work happening, but it could have happened 5 years ago, or even more if we had known that. But roadmaps are all we've got. They're still needed, but they may not turn out to be right. So let me shift to a different topic. So talk about where things are today. Now we are now at exascale. So where things stand today from the application side, and then going forward as well, and then from the technology and system side, and from MPI itself. So from the applications side, it's too bad that the title is being cut off here, but the people on Zoom can see it better. The exascale computing project, which started in 2016, is now in its 6th or 7th year, and it'll end in another year in 2023. And it has funded a whole bunch of application projects, and these are running at exascale, or they're getting ready to run at exascale. So these are an example of large scale applications today. So ECP has codes. There are 24 application projects, and they span national security. They span energy security, design of nuclear reactors and combustion engines and fossil fuels and so forth. There's additive manufacturing. There's scientific discovery, cosmology. The hack code is there. There is other stuff, climate and metagenomics and so forth. And there are 24 projects which are fairly large, funded at $3 million a year or more than that in some cases. They're large efforts, but there's 78 separate codes in those applications, and they represent over 10 million lines of code, probably way more than that. And there are, in many cases, large user communities that use those applications. And when they started in 2016, those codes already existed in most of them already existed. They started out as either all MPI or MPI plus OpenMP on CPUs, and most of them did not have a GPU version. So a lot of that had to be done during this time frame. So let's look at what kind of programming models do they use. So almost all of them for communication use MPI. So what that means is MPI is still predominant at exascale, despite the naysayers. 20 years ago, people would say MPI could not possibly be used at petascale. And then 10 years ago, people would say that MPI could not possibly be used at exascale, but yet it is the predominantly used for the internode or interprocess communication part. There are a few codes that use other communication methods. So there's the ExaBiome project out of Berkeley, which is one of the application codes. That is a UPC++ code, UPC++ GasNet. So it uses the PGAS model. Then one of the codes in the ExaFEL application, which is free electron lasers out of SLAC, uses Legion. And Legion is also from Stanford, and they're part of that team. Then there are some parts of NWChem EX are using Parsec, but they also have other MPI and other versions. So there is a small amount of exploration with other projects or usage, but MPI is, probably 75 out of those 78 codes of that order are MPI. At the intranode programming model level, that is, how are they using the GPUs? Things are a lot more complex, and there isn't one solution there. They are all using different methods. So they use either GPU specific kernels, that is, they have abstracted their application code into kernels which they have written in CUDA or HIP or SYCL or sometimes multiple of these, so that they could run separately on different systems, and that this took a lot of work to do it efficiently and get the code in that form. Or they're using directive-based approaches such as OpenMP or OpenACC, and the Fortran codes tend to use this. Then a third method is C++ abstraction. So you must have heard of the COCOS and Raja efforts, which are high-level C++ and the performance portability abstractions, where if you use those C++ based features, then there are backends that will do the job for you to on different GPUs and even on multi-core systems. So there are many applications using that. And others use libraries or co-design frameworks that are also part of ECP, such as the AMR, Adaptive Mesh Refinement, AMRX, and they do the GPU. They are implemented to use the GPU, so they take advantage of libraries to do that. And each year, the application development group in ECP, they produce a report, that is like a 200-page document, which is a good read in itself if you want to understand what those codes are doing, not just from the science side, but they talk about their, the computing aspect of it, also the algorithms and what they use. The last page of that report, there is an appendix that actually lists all the codes and what programming language they use and what GPU programming model they use. They don't even mention MPI in that appendix because that's so pervasive that it's not worth the additional column. So I have two slides of this because it doesn't all fit in one slide. So on the left is the project, and each project has 3 or 4 codes. So the next is the code name. Then is the programming language that they use. So you'll see there's a mix of Fortran and C++. And 3-4 years ago, there was more of Fortran in this column, but these applications have ported to C++ now to take advantage of things like COCOS and Raja. So you're seeing a lot more C++ here. And on the GPU programming model side, there is no one solution that's commonly used. They're using multiple. So you see OpenMP, you see OpenACC, Raja, COCOS, CUDA. Some of them are using the AMREX and other libraries. What else is there? OpenCL is also there. Then on the next slide, there's a similar story, mix of C++, and here you see languages like Python and Julia as well. There's a little less of Fortran here. And the Python is used by that one code called Candle, which is actually a deep learning application. So that's the one big project here that is an AI project. The others are mostly traditional simulation type of code. So this one uses TensorFlow and PyTorch and Python. And as I said, the XIFEL there is one Legion usage, and there are COCOS and Raja are being used there. And if you actually draw the graph of what is being used, Fortran is a small number now. There are 14. C++ are 64, and Python is 4. And the GPU programming models is a whole variety. There's no convergence there. They're trying different things. So the situation with the GPU programming models is similar to what it was with when MPI came into existence. In 1992, when MPI started, and when I was a graduate student, there were so many different message passing libraries that you could draw a similar graph with what application codes were using in terms of message passing. But then when MPI came along, everyone has pretty much switched to using MPI. I think it's a harder problem with the GPU programming models. There might be some convergence in the future, but I doubt it'll be converging to one like MPI. There might still be 2 or 3 or maybe even more in that space. And in support of these ECP applications, ECP also supports software development. And one area in that is the programming models and runtimes, which I I'm the lead for this area. And this supports development of supports 2 MPI implementation efforts. MPitch and OpenMPI are both, and these are fairly large efforts. And hopefully it'll continue even beyond next year, because ECP ends September of 2023. And hopefully the DOE will continue funding in some way. We don't know as yet, but I would love to see all these projects going forward at a similar scale. In addition to MPI, ECP supporting the Legion and Parsec, which are like task-based programming models. One is out of Stanford and the other is at UTK. There is UPC++, the PGAS model as well. And then there are the COCOS and Raja efforts, which started even before ECP, and they were funded by the NNSA labs. But ECP is also funding them because many applications use them, and they need the more targeted back-end development for Frontier and Aurora. So that work is happening. And there are many labs involved in that. And there are other memory management and power management efforts, the SICM and Argo. There's also a big OpenMP project, the SOLVE project, which was led by Barbara Chapman until she moved to HPE. And it's now Sunita Chandrasekaran is leading that. That is actually been moved into the development tools area because it's LLVM based and there are other LLVM projects there. So in addition to programming models and runtimes, there are efforts in tools, which, as I said, there's a lot of LLVM work happening there. OpenMP, there's also OpenACC, and there's a Flang to support Fortran through LLVM. And there are lots of tools-related efforts. There's math libraries, data and visualization packages, which has things like HDF5 and efficient checkpoint restart and compression and so forth. And there are other efforts related to packaging and containerization. And so you can download all this through the e4s.io website, and it's containerized, and you can easily download and use it. So in terms of the application usage summary, for the traditional MPI, traditional simulation codes, MPI is still predominant, and it's likely to remain so. And I don't hear complaints from the application groups about MPI per se. I don't hear anyone saying we need something other than MPI for their code. They're already using MPI. It's already in many cases abstracted out in some way. It doesn't bother them. The complaints are that I hear are they can be called implementation issues, or sometimes it's even an installation issue, that something about the installation breaks, and there's some new version of some other software that causes problems even in MPI. And you'll hear some stories from Al Geist on Wednesday about that on Frontier. And the implementation issues are performance. Sometimes the collectives are not working as well as they should, or scalability issues, or just bugs in the implementation. And of course, efficient GPU support, which is it's relatively new in MPI, so there can be problems there. Then there are another set of applications that are in the AI space that also need communication. Particularly, they're doing all reduces, collectives. But as far as I can tell, they're not using MPI as such. They're using Nickel, the NVIDIA library, or they're writing their own. And I see papers from the AI people on archive about tuning collective communication. And I feel that MPI could play a role here, and MPI has done collectives for ages, and we could do better so as not to miss that whole space that is emerging. And we probably need a better job with GPUs and matching the actual hardware that the AI guys are using. But there's an opportunity here. Okay, so that was from the application side. So from the technology and system side, what's happening. We've reached exascale. There's one system already, on the top 500, and it's going to be in production soon. And 2 more systems are coming in the next year or so. But that doesn't mean it's the end of the road. There is post exascale activity is starting, and I'll talk a little bit about that. And in terms of what we can expect, I have not seen too many roadmaps or architecture studies like last time. But the best we can say is, expect more heterogeneity on the nodes and more specialization and more specialized accelerator types, not just GPUs, but others. There could be AI accelerators on the node. So the hybrid programming becomes even more important, and the activities of the hybrid working group are important. And the efforts to reach the next 1,000-fold increase in performance, which is zetascale, although we don't hear that word as much as we used to hear exascale for such a long time. But it's coming, and I'll tell you why. And there are significant power challenges to be solved there. That is, how do we get to 1,000-fold performance without even a 100-fold increase in power, or even a 10-fold increase in power, because that will be too expensive for us to afford. So there's microelectronics research to be done there, and along for that toward that end, there's some recent developments. So there was this Chips and Science Act passed in the U.S. a month or a little more than that ago, and which is supposed to develop capability in the U.S. in microelectronics, both manufacturing as well as R&D. In response to that, the PCAST, which is the President's Council of Advisors on Science and Technology, which is a very high-level group of advisors to the president, they wrote a letter in early August, which to offer recommendations on how some of the budget from that Chips and Science Act could be used for semiconductor R&D. And this was a 3-page letter, and the third, which you can find that online, and the third page, they recommend several that the nation start a set of new grand challenges to ensure that the U.S. leads the world in innovation. But they specifically call out, for example, the U.S. should be the first country to build a zetascale computer, which would be 1,000 times faster, and what such a computer could achieve. And just last week, like last Thursday or Friday, they issued a report, which is like a 30-page document, bigger than that letter, which was about revitalizing the U.S. semiconductor ecosystem, which had more detail about what could be done in the microelectronics. And again, they repeated that we recommend that a set of grand challenges, and the first one is advanced computing into the zetascale area, where they again said U.S. should be the first to build a zetascale computer. Now, when a high-level body like this puts such a thing out, it doesn't go unnoticed. It trickles down, and the agencies like DOE and NSF and DARPA and others will start incorporating this into their priorities, and we will see funding opportunities to get to zetascale and the R&D needed there in microelectronics and so forth. And if you look at who's on the PCAST, these are very high-level people, but the 2 names I recognize there because they're from the computing side are Bill Daly from NVIDIA and Lisa Su from AMD. She's the CEO of AMD. So I would think that they were instrumental in getting this language into this report, because they are the computing people. So, and they're from industry. So the industry is also supportive of this. So, we will see more activity towards zetascale. On a more practical side, a few months ago in June, the DOE labs issued an RFI, a request for information on it was called Advanced Computing Ecosystem. So an RFI is something that the DOE labs issue to industry to get responses from industry, and it's just information. This is not a funding opportunity. So now that the DOE has reached or is reaching exascale, what's next? They want to know. They want to make plans for the future for their next system. So this this call, which is also online and you can download it, asks for vendors to provide information about their roadmaps and their plans of about where they are going, where they see the technology going, and the systems. And there are like about 30 or more vendors responding to this. So they're even smaller component manufacturers and not just the whole technology people. And this RFI also says what DOE thinks the future systems would be. So it says our rough estimate of targets includes traditional HPC systems in the 10 to 20 FP64 exaflops level in the 2025 plus time frame, and 100 plus FP64 exaflops in the 2030 plus time frame. So that's 8 times today's systems in 2026 and 64 times today's systems in 2030. So DOE has plans of getting systems of that size. And if you're at 100 plus exaflops in 2030, you are now close to, approaching zettaflops in the next few years. I mean, we're at getting to the doorstep of that. So, there will be activity towards this, and exascale we have not reached like an endpoint or anything here. So as far as I can tell, it's the hybrid type of programming is important, and there's lots of other stuff happening also in MPI that is important, such as the async proposal that Quincy has, and even some of the fault tolerance things. Now about MPI itself, if you look at the MPI standard, it is, as it has evolved, it keeps getting bigger. So MPI 1 was 230 pages and 128 functions. Then 2.2 is 623 pages and 325 functions. MPI 3 was 822 pages and 400 functions. And now MPI 4, we are at 1100 pages and 525 functions plus another 150 large count functions. And these function counts may not be exact because I couldn't count them, and someone helped me with it. But what it says is it is getting big, 1100 pages. And although the number of functions should not be an issue, and which we have been saying for a while, because the functionality is orthogonal and the users can look at what they need, it's still it has two problems. Is that there is an implementation burden. There are limited resources for developers, and they get used to optimize a few things. And there's a lot of functionality to carry forward. And users are also intimidated by the size of it. So we give a lot of tutorials, and there you get at best 1 day for a whole day for the tutorial, which is like 6 hours. And even if you restrict it to advanced MPI, it's not enough to cover everything in advanced MPI. And some of the things are so complex that it's hard to teach those, and it's not clear that all the attendees need all of it as well. So there is a lot of stuff there. So how can we keep MPI nimble? So most of MPI was designed 25 to 30 years ago in the 90s, basically. And for systems of that era, which were a different set of systems. And since then, we have been sort of retrofitting additions to it, or fixing problems in it, or adding chapters to it. But if MPI were designed from scratch today, it may not have some of the functionality it does. It may not have all those variety of send modes that it has. And there's so many other things you could point out that may not be there. So to make future additions to MPI feasible, I mean, let's say 30 years have gone by, how about the next 30 years? It may make sense for the MPI forum to undertake an effort to see what could be deprecated from MPI without causing too much trouble. And I would say that there could be a working group, and with sufficient time frames, say 12 to 18 months, could be even more. But they have to look at it carefully and deliberately, not willy-nilly and say, okay, I don't like this, let's get rid of this. It has to be done little more carefully to see what could be deprecated, because it's no longer useful, and it won't bother too many applications. Maybe some may need to change, but I think that might help in keeping it extensible without the implementation burden of carrying everything forward, and also easier on users. And one last bullet that I've added is we need to keep the vendors actively engaged in MPI standard as they were for MPI 1 and 2. And what I mean is in MPI 1 and 2, the vendors were, they were almost like gatekeepers, and you couldn't get a new feature in without they being actively involved. And there were many vendors in those days because there were so many. There's been consolidation, and usually the head of their MPI library development or their chief architect used to attend and make sure that nothing gets in that would be difficult for their machine or not work well or so forth. And I felt, and I could be wrong, that after that, MPI 3 and onwards, there was less of vendor. And there were vendor people, but they may not have been the ones developing the MPI there or responsible for developing the MPI there. And the vendors are sort of relying on the open source implementations that the open source ones will develop the latest version of the standard, and they will get that. They also rely on the procurements and what they specify, and the procurements are somewhat lagging behind. Procurements ask for MPI 3 when MPI 4 is already out and so forth. But I think it would be good if we can get the MPI developers from the vendors engaged and to make sure that things don't get added there that may not be right for the upcoming hardware and so forth. Just changing topics a little bit, I wanted to point out to some work that has existed for some while but may not be well known. So this is a formal model for MPI 3 RMA. You cannot see the title here, but the Zoom people can see it. So a formal model for MPI 3 RMA has existed since at least 2015, maybe a year or two earlier. It's a paper published in ACM Transactions on Parallel Computing. So Torsten sort of spearheaded this effort, but involved many of us. It's fairly complex. It's written in a language that the formal model folks could understand. And it was intended to be used by tools. The tools could use this formal specification to verify implementations and so forth. But I don't think such a tool has been written, as far as I know. So there is room for tool development along these lines. When you undertake such an effort, there is always a possibility that not all of the MPI RMA specification is captured by that formal model. And it's so subtle that some of the subtleties may be missed, and that's always a risk. But a lot is there, and even if that could be checked and verified, would be useful. A different thing, which is simpler, is something called self-consistent performance guidelines for MPI that Jesper Larsen Traff kind of spearheaded. This was also about 10, 12 years ago, but Bill and I were also involved in this. And this lays out some common sense performance expectations out of MPI. And it's somewhat, we call it self-consistent in the sense that it is defined in terms of MPI functionality. That is, one MPI function, a single MPI function, should not perform worse than some combination of other MPI functions that implement the same functionality. Or a specialized function should not perform worse than some general function that can do the same thing. So, for example, an all gather should not perform worse than a gather plus a broadcast, or a scatter should not perform worse than a broadcast because it's you're doing less work. And there are many such sort of guidelines laid out in that paper, and there could be more. And the idea was that a tool could systematically check for these. And the paper has results that shows that many of these are violated by implementations at that time. These are simple things so these are what are called, I would call surprises, performance surprises that applications don't expect. But a tool could be written that checks for this and is part of the nightly testing and reports on it. But I haven't seen a tool developed to do this. But that would be a lot easier than that formal model one that I showed. Interesting paper to be presented at SC22 in a couple of months. I was not directly involved in this, but Rohit Zamre, who was a student at UC Irvine, and he was also at Argonne as a student for a couple of years, he and his advisor have written this paper. So this is good for anyone who is interested in MPI plus threads to read, because it's a very detailed comparison of the various approaches to support MPI plus threads. That is, endpoints or partitioned operations or distinct communicators. and it's written from an applications perspective as well, what it means for from applications. And they have outlined a set of 20 lessons, literally a lesson 1, 2, 3, 4, all the way up to 20 about what this is. And Rohit's thesis was in this area, and he also got the ACM SIG HPC doctoral dissertation award last year for that thesis. So it's quite it's a good paper for the hybrid programming working group, or anyone interested in MPI plus threads to look at it. Rohit could send it to you. I could also send it to you. He sent me a copy. Some more recent work in our group is on auto-tuning collective communication using machine learning. So we have a very good student, Mike Wilkins from Northwestern. So this is a collaboration between Argonne and Northwestern, and Peter Dinda and Nikos Hardavelas from Northwestern. So the idea here is, there are collectives in MPI use many algorithms, and there are different cutoff points for different message sizes and system sizes and so forth. How do you pick the right algorithm? So this one, instead of doing an exhaustive search, this one tries to do things more intelligently and by reducing the training time in the machine learning. And Mike has published 2 papers on his. One was at EuroMPI last year, and the other was at Cluster just earlier this month in Heidelberg that he presented. And another paper I just want to mention, it'll be presented at 1:30 this afternoon, that Hui is going to present. It's about MPI X streams. And this is a unified approach for supporting both MPI plus GPU streams and also MPI plus threads. And it's an extension to MPI, and that's why it's MPI X is what we call it. And it'll help help with mapping MPI plus threads more efficiently to network endpoints. And also it'll help making the GPUs, support GPUs better and minimize synchronization between the GPUs and the CPU for the streams case. And there was also another paper that the HPE group, the Cray MPI group, uploaded to arXiv just a month back. That is, tries to solve the same problem in a slightly different way. They call it MPI XQs, and they have a slightly different API. But that's also worth reading. And these are things for the hybrid or accelerator working group to consider. And they are already, this has already been presented there and it's under discussion. And one last slide was a tribute to Rusty. As you know, Rusty passed away in May of this year. He was one of the founders of the MPI forum, and he started the MPitch project back in 1992 with Bill, and Tony was also part of MPitch in the beginning in those days. He also chaired MPI 2 in the mid 1990s, and that's where I got to know Rusty. I joined Argonne right at the time where MPI 2 was starting. And he was a close friend and collaborator and mentor to many of us, certainly to me. He was also a true believer and a true champion of MPI. He really thought that MPI was a good thing in the world of parallel computing. And one of his last interviews, which you can find online, was called "The Keys to Success: Good Projects, Good Choices, Good Collaborators, and Openness to Change." So this is not a video interview; it's a text. It's a web page. So if you just search for Rusty Lusk and the keys to success, you'll find it. It's a good read. It's typical Rusty. And in honor of Rusty, we're organizing a research symposium to be held at Argonne in the spring in April, and tentatively it's April 13th to 14th. It's in the early stages of planning right now. And I know that Tony also is planning a tribute to Rusty at this week on Wednesday. So that's about it. Just to conclude, MPI has survived and I would say has thrived for 30 years despite some of the disbelievers. And I think it will continue to thrive going forward. But we need to keep an eye on some things. One is I think over the next 30-year period we should keep the standard from getting too big. And one way to do that is to carefully deprecate unneeded stuff, and that's what I suggested. We should keep the vendors actively engaged as they were in MPI 1 and 2 days. Be responsive to changes in technology and systems, as say the Zeta scale emerges and what's going on there, and there could be some surprises or things that we don't know right now. And try not to lose the AI applications to other communication methods, other ways of doing what MPI can do or MPI has been good at for so long. So that's all I have, and I'm happy to take any questions. I thought this was the microphone. Oh, there's another one. I can repeat the question for the Zoom meeting, or even from Zoom. Oh, there's a chat. Yeah, let me see. Okay. We will have a discussion on these approaches to GPU streams in the hack working group meeting this week. Okay, at the MPI forum. Good. And no, this was just. Yeah, I think that's it there. Yeah. 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 No, MPI will still survive because in a distributed computing world, we'll need to write portable applications that do communication. But the MPI library will need to work in that kind of mode where there'll be more of offloading communication to all these other, to the DPU or other things, and what parts of the MPI stack could be run on those things and what run on the CPU, and moving data efficiently in that context from the GPU memory or other memory directly to its destination needs to be done. So it gets into implementation issues and maybe some aspects of the specification that would enable that, or at least don't come in the way of that. And yeah, the vendor would provide a lower level solution for sure. And to the extent we can leverage that and layer MPI on top of that would be good. Yeah. 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 So they're not happy because they don't use all of MPI. They are happy even though they don't use all of MPI. Yes, there is opportunity for them to use, and that's what we try to tell them in our advanced MPI tutorials, that you could use this feature and that feature. Sometimes the performance that implementations provide for some of these advanced features is not up to the mark, and that's a chicken and egg problem because no one's pushing them. That the applications are not pushing them to tune or optimize that part. But there is opportunity, like even MPI RMA is not used as much as it could be. Some of the MPI 4 features are not used as much as they could be. Partition communication, the new stuff. Yeah, but there is also the chicken and egg stuff that the implementations lag behind because nobody's pushing them. The vendors will do, they'll beat all their benchmarks and the procurement, whatever is required for that. So maybe those benchmarks need to use modern features. Yeah. Yeah. Okay, I thought somebody might ask. Top 3 features for deprecations. One is all the send modes in MPI, the ready send, synchronous send, buffered send. Probably not, if MPI was designed today, I don't know if it would have all that. I don't see apps using that. The other MPI libraries at the time had those features, so they were there. In the IO chapter, there are some things that could be deprecated, the shared file pointer and the the user-defined external representations and for the derived data types, they don't get used very much. In the RMA chapter, there is stuff that could be deprecated, like the post-start complete wait synchronization, maybe even fence, but it's so simple that we might want to retain that. The dynamic process chapter is also not used so much, and so there could be parts of that could be deprecated. But I think that's why I said a more systematic effort is needed, and looking at getting input from applications as well, and from the vendors, because they know what is used. Yeah, so standardization is always, it takes a lot, and MPI is faster than some of the other standards like C++ and the ISO and others. So vendors are used to that. That is both good and bad. And the good is that random things don't easily get in. But we should feel free to use the MPI X, experiment with new features and have implementations. So one of the things that is lacking is that new features may not have implementations that demonstrate how good they are. And if that is there, I think it's easier to get things into the standard, because now there is an existence proof that anyone, there will be less pushback on new features when something has been implemented and demonstrate to be useful and effective. But it won't be as fast as the Nichols and the others can, because they can just add things. If there is one. Yeah, but the vendor would be vendor specific. So MPI is portable. That is the advantage.